Hello and welcome to Science After Dark. Before we begin tonight's journey, take a moment to like the video and subscribe to the channel if you enjoy calm explorations of the universe. And while you're settling in, let me know in the comments where you're watching or listening from tonight. Whether you're in a quiet apartment in a busy city, a small town under dark skies, or somewhere far out in the countryside where the stars are easy to see, it's always fascinating to think that the light above you began its journey billions of years ago. In a way, every place on Earth has its own view into the deep past of the cosmos. Tonight, we're going to follow one of the quietest but most powerful stories in the universe, the story of how gravity built the first galaxies. If you step outside on a clear night and look up, you might see the faint band of the Milky Way stretching across the sky. That soft glow is made of hundreds of billions of stars, arranged in a vast rotating system nearly 100,000 light-years wide. And yet, as enormous as it feels, our galaxy is only one among trillions scattered throughout the observable universe. But the universe did not always look like this. There was a time, long before galaxies, long before stars, long before planets or life, when the universe was almost perfectly smooth. No spirals of starlight, no glowing nebulae, no galaxies at all. Just a vast, expanding ocean of hot particles and light. And yet, hidden within that smoothness were tiny imperfections, subtle fluctuations in density so small that they would have been impossible to notice at the time, slightly denser patches here, slightly emptier regions there, differences so small they were measured in mere fractions of a percent. At first glance, these tiny irregularities might seem insignificant, but the universe has a remarkable way of turning small differences into enormous consequences. Because wherever matter was even slightly denser, gravity began to pull, very slowly, almost imperceptibly at first. A region that contained just a little more matter than its surroundings would begin attracting nearby gas. That extra matter would strengthen its gravitational pull, drawing in even more material. Over time, this gentle process would repeat again and again, quietly amplifying the original imbalance. Millions of years passed, then hundreds of millions. Gradually, the smooth universe began to change. Matter gathered into enormous invisible structures made largely of dark matter. Vast gravitational frameworks stretching across space like the scaffolding of a cosmic city yet to be built. Gas flowed along these structures, collecting in dense pockets where the first stars would eventually ignite. Those early stars would burn brightly, live briefly, and explode violently, scattering the first heavy elements into space. And from those enriched clouds of gas, the first galaxies would slowly emerge. Some would become small and chaotic collections of stars. Others would grow through mergers and gravitational encounters, forming vast rotating systems, spiral galaxies like our own Milky Way. But none of this happened quickly. Gravity is not a force of sudden drama. It is patient, relentless, and over billions of years it can transform the faintest whisper of matter into some of the largest structures in existence. Tonight, we'll follow that transformation step by step, from the nearly featureless universe shortly after the Big Bang, to the delicate quantum fluctuations that seeded cosmic structure, to the invisible web of dark matter stretching across space, and finally to the birth of the first galaxies, great rotating islands of stars shaped by gravity's quiet persistence. So dim the lights, settle in, and let your mind wander out into the deep universe. Because the story of galaxies is not just a story of stars, it's the story of how gravity slowly built the architecture of the cosmos itself. Long before galaxies existed, before stars lit the darkness and before planets formed around distant suns, the universe was an astonishingly simple place. If you could travel back far enough in time, to the first few 100,000 years after the Big Bang, you would not see the rich cosmic landscape we observe today. There would be no glowing spiral galaxies drifting through space, no clusters of stars, and no immense clouds of gas illuminated by stellar light. Instead, the universe would appear remarkably smooth. Matter and energy filled space in a nearly uniform sea, stretching in every direction as the universe expanded. The temperature was still extremely high by modern standards, and the cosmos was filled with a dense mixture of particles and radiation. Photons, electrons, and atomic nuclei constantly collided with one another in a hot glowing plasma. To our modern perspective, it might seem surprising that such a simple beginning could eventually produce the complex cosmic structures we see today. Yet this picture of a young, smooth universe emerged gradually through the work of several pioneering scientists. In the early 20th century, the Belgian physicist and priest Georges Lemaître proposed a bold idea. He suggested that the universe had begun in a much denser and hotter state, expanding outward over time. Around the same period, the Russian mathematician Alexander Friedmann developed mathematical solutions to Albert Einstein's equations of general relativity, showing that an expanding universe was not only possible, but a natural outcome of the laws of gravity. At the time, these ideas were radical. Many scientists believed the universe was static and eternal, neither expanding nor changing on the larger scales. Even Einstein himself initially introduced a modification to his equations to prevent the universe from expanding. But observations would soon force the issue. In 1929, the American astronomer Edwin Hubble carefully measured the light coming from distant galaxies. By studying how their light was shifted toward longer wavelengths, a phenomenon known as redshift, he discovered something extraordinary. Galaxies were moving away from us, and the farther away they were, the faster they appeared to recede. The simplest explanation was that space itself was expanding. If the universe was expanding today, then in the past it must have been smaller, denser, and hotter. This realization laid the foundation for modern cosmology and the theory we now call the Big Bang. As the universe expanded, its temperature gradually dropped. During the earliest moments, matter existed as a seething plasma in which light could not travel freely. Photons constantly scattered off charged particles, making the universe opaque, more like a glowing fog than the transparent space we experience today. But after several 100,000 years of expansion, conditions changed. The temperature fell to a point where electrons could finally combine with atomic nuclei to form neutral atoms, primarily hydrogen and helium. This event is known as recombination. Once atoms formed, photons were able to travel long distances without constantly scattering. The universe became transparent. The faint glow from that moment still fills the cosmos today as the cosmic microwave background, a gentle afterglow of the early universe that astronomers continue to study with remarkable precision. Yet even in this newly transparent universe, something curious was already present. The distribution of matter was almost perfectly uniform, but not entirely. Tiny variations existed in density. In some places, matter was slightly more concentrated. In others, it was slightly less so. These differences were incredibly small, often amounting to variations of only a few parts in 100,000. At first glance, such tiny fluctuations might seem trivial. But in cosmology, even the smallest irregularity can grow into something vast. Understanding how these minute differences evolved into galaxies required the development of a powerful theoretical framework known as cosmological perturbation theory. Among the scientists who made major contributions to this field was the Russian physicist Vladimir Mukhanov. Perturbation theory treats the early universe as a nearly smooth background, with small disturbances layered on top of it. Instead of studying a perfectly uniform cosmos, physicists examine how these slight deviations behave under the influence of gravity and cosmic expansion. Mukhanov and other cosmologists showed that small density variations could grow over time. Regions that contained slightly more matter exerted a slightly stronger gravitational pull. That extra gravity would attract additional matter from the surrounding environment. The process was subtle but relentless. A region that began only slightly denser than average would slowly accumulate more material. As it grew heavier, its gravitational influence increased, drawing in even more gas and dark matter. Over vast spans of time, this quiet accumulation could transform tiny fluctuations into enormous cosmic structures. It is important to recognize just how small the original irregularities were. If the early universe was scaled up to the size of Earth, the density variations that eventually produced galaxies would be comparable to gentle ripples only a few centimeters high on an otherwise perfectly smooth ocean. Yet gravity has an extraordinary ability to amplify such modest beginnings. Unlike forces that fade quickly or depend on complex interactions, gravity simply responds to mass. Wherever matter gathers, gravity strengthens. Wherever gravity strengthens, more matter is drawn inward. This creates a feedback process that unfolds gradually across millions and then billions of years. The early universe did not erupt suddenly into galaxies. Instead, structure emerged slowly and patiently. Small fluctuations grew larger. Slightly denser regions gathered more material. Gradually, these regions became the gravitational wells that would one day host the first stars in the earliest galaxies. Gravity, in this sense, acts less like a dramatic sculptor and more like a patient gardener. Given enough time, it nurtures tiny seeds of structure until they grow into vast cosmic systems. By the time the universe was several 100 million years old, these once subtle irregularities had begun to transform the smooth cosmos into something more complex. Invisible frameworks of dark matter were forming. Gas was starting to collect in gravitational pockets. The stage was quietly being set for the ignition of the first stars and the birth of the first galaxies. All of it began with a universe that was almost perfectly uniform. Almost. The early universe may have appeared smooth on large scales, but its true origins were anything but calm. To understand where the tiny density variations came from, the ones that would eventually grow into galaxies, we must travel even further back in time, back to an era so early that the universe was less than a fraction of a second old. At this point in cosmic history, the entire observable universe was unimaginably small. All of space, all matter, all energy, compressed into a region far smaller than an atom. The laws of physics as we understand them were already operating, but under conditions of temperature and density so extreme that familiar structures could not yet exist. In the late 1970s and early 1980s, physicists began exploring an idea that would radically reshape cosmology. This idea was known as cosmic inflation. The concept was first proposed by the American physicist Alan Guth in 1980. Guth was attempting to solve several puzzling features of the Big Bang model. One of these puzzles was known as the horizon problem. When astronomers observe the cosmic microwave background, the faint afterglow of the early universe, they find that regions of the sky separated by enormous distances have almost exactly the same temperature. Yet according to simple expansion models, these regions should never have had time to exchange information or energy. Inflation provided a possible explanation. Guth suggested that in the earliest moments after the Big Bang, the universe underwent a brief but extraordinary period of accelerated expansion. During this phase, space itself expanded at an almost unimaginable rate. In an incredibly small fraction of a second, the universe expanded by a factor of at least 10 raised to the power of 26. To picture this, imagine an object the size of a proton suddenly expanding until it became larger than a galaxy. Other physicists soon expanded on Guth's idea. The Russian physicist Andrei Linde developed several versions of inflationary theory that made the mechanism more stable and flexible. Around the same time, the Soviet physicist Alexei Starobinsky proposed a related model in which inflation emerged naturally from certain properties of gravity itself. Together, these ideas formed the foundation of modern inflationary cosmology. At first glance, inflation might seem like an abstract concept designed mainly to tidy up mathematical problems. Yet it carries a remarkable implication. Inflation does not merely smooth the universe. It also explains where the tiny irregularities in matter density came from in the first place. To understand this, we must step into the strange domain of quantum mechanics. On extremely small scales, nature is never perfectly still. Even in what we might call empty space, tiny fluctuations constantly appear and disappear. These fluctuations arise from the uncertainty inherent in quantum fields. In everyday language, one might imagine the fabric of space as quietly trembling with microscopic disturbances. Normally, these fluctuations remain confined to unimaginably small scales. They appear briefly and then vanish again without leaving any noticeable trace. But during the period of cosmic inflation, something extraordinary happened. The rapid expansion of space stretched these tiny quantum fluctuations to vastly larger sizes. A disturbance that began at a scale smaller than an atom could suddenly be expanded across cosmic distances. Inflation effectively magnified microscopic irregularities until they became macroscopic features embedded in the structure of the universe. This idea was explored in depth by the physicists Vyacheslav Mukhanov and Gennady Chibisov in the early 1980s. Their work demonstrated that quantum fluctuations during inflation would naturally produce small variations in the density of matter and energy throughout the universe. These variations were not random in a chaotic sense. Instead, they followed predictable statistical patterns. Mukhanov and Chibisov showed that inflation would produce what physicists call density perturbations, slight differences in the distribution of matter that could later grow through gravitational attraction. Their calculations revealed that the fluctuations should have a particular spectrum of sizes and strengths, one that could eventually be tested through astronomical observations. Decades later, measurements of the cosmic microwave background by satellites such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft confirmed these predictions with remarkable accuracy. The tiny temperature variations seen in the microwave background are direct evidence of those early density perturbations. The statistical properties of these fluctuations can be described using a concept known as a Gaussian random field. In simple terms, this means that the density variations across the early universe followed a pattern similar to a bell-shaped probability distribution. Most regions had densities very close to the average value. Only a small number of areas were significantly denser or emptier than their surroundings. If one could somehow map the early universe in 3 dimensions, the pattern would resemble a gentle landscape of hills and valleys. The hills represent slightly denser regions, while the valleys represent slightly less dense ones. These hills and valleys were incredibly shallow. The typical variation in density was only about 1 part in 100,000. That means that if the average density of matter in the early universe were represented by 100,000 grains of sand, the difference between a dense region and an average region might amount to only a single extra grain. And yet, these tiny statistical differences contained the blueprint for every galaxy that would ever exist. Where density was slightly higher, gravity would slowly begin to pull matter inward. These regions would gradually deepen their gravitational wells, drawing in gas and dark matter from surrounding space. Where density was slightly lower, matter would slowly drift away, leaving behind vast, expanding regions of emptiness that astronomers now call cosmic voids. Over hundreds of millions of years, the gentle pattern established by quantum fluctuations would evolve into the enormous structures we observe today. The filaments of the cosmic web, the clusters of galaxies containing thousands of stellar systems, and the rotating galaxies themselves, each containing hundreds of billions of stars. It is remarkable to consider that these vast structures began as tiny disturbances in the quantum fields of the early universe. The galaxies that fill the night sky are, in a very real sense, the magnified remnants of microscopic fluctuations that occurred when the universe was less than a second old. The entire cosmic landscape emerged from this delicate interplay between quantum uncertainty and cosmic expansion. Inflation stretched the fluctuations, physics shaped their statistical pattern, and gravity, patient and persistent, would eventually transform them into the great gravitational wells where galaxies could form. From those humble beginnings, the universe began its long journey toward complexity. The early universe contained only the faintest hints of structure. Tiny variations in density, born from quantum fluctuations and stretched across space during cosmic inflation, created a subtle landscape of slightly denser regions and slightly emptier ones. At first, these differences were incredibly small, barely distinguishable from the average background of matter filling the expanding universe. But even the smallest imbalance can become important when gravity is involved. Gravity has a very simple rule. Any concentration of mass attracts other mass, and once matter begins to gather in one place, its gravitational pull strengthens, drawing in even more material. Over long spans of time, this simple principle can transform small irregularities into vast cosmic structures. This process is known as gravitational instability. The concept is elegantly straightforward. Imagine a region of space that contains just a little more matter than its surroundings. Because it contains slightly more mass, its gravitational pull will be slightly stronger. Nearby gas and dark matter will feel this additional pull and begin drifting inward. As matter falls into this region, its density increases further. That increase strengthens the gravitational attraction even more, encouraging additional material to join the gathering cloud. In other words, gravity creates a feedback process. A small advantage in density becomes amplified over time. Meanwhile, the opposite happens in slightly less dense regions. Matter gradually drifts away from them, making them emptier still. Over billions of years, this quiet separation between dense and empty regions gives rise to the enormous cosmic web of filaments, clusters, and voids that astronomers observe today. Although the idea sounds intuitive, scientists eventually wanted a precise mathematical description of when gravitational collapse would actually occur. Under what conditions would a cloud of gas continue expanding with the universe, and when would gravity overcome that expansion and begin pulling matter together? The first rigorous answer to this question came from the British physicist and astronomer Sir James Jeans. In 1902, Jeans developed a theoretical model to study the stability of gas clouds under the influence of gravity. His analysis considered two competing forces acting within a cloud of gas. One force is gravity, which attempts to pull matter inward and compress the cloud. The other is pressure, generated by the random motion of particles within the gas. Pressure acts outward, resisting collapse. Jeans showed that if a gas cloud becomes sufficiently large and massive, gravity can overpower the internal pressure trying to keep it spread out. When this happens, the cloud becomes unstable and begins to collapse. This idea became known as the Jeans instability. Jeans derived a characteristic scale that determines when collapse occurs. Physicists refer to this as the Jeans length, which represents the minimum size a gas cloud must reach before gravity can overcome pressure support. In simple terms, if a cloud of gas is smaller than the Jeans length, pressure forces dominate and the cloud remains stable. But if the cloud becomes larger than the Jeans length, gravity takes control and collapse begins. Jeans also described a related quantity known as the Jeans mass. This represents the minimum mass required for a region of gas to become gravitationally unstable. The equation describing this threshold can be expressed in words as follows: Jeans mass equals the cube of the sound speed within the gas, divided by the gravitational constant, raised to the power of 3/2 multiplied by the square root of the density of the gas. While the mathematical details are complex, the key idea is simple. Collapse occurs when gravity becomes stronger than the pressure resisting it. In the early universe, enormous clouds of hydrogen and helium gas filled space. As the universe expanded and cooled, the sound speed within this gas gradually decreased. Lower sound speed meant weaker pressure support, which in turn reduced the Jeans mass required for gravitational collapse. Over time, regions that once remained stable began to cross this threshold. Gravity could now pull matter inward more effectively. As these gas clouds slowly contracted, their densities increased. With higher density came stronger gravitational attraction, which accelerated the process further. The collapse of matter was not perfectly smooth, however. The universe contained both ordinary matter and dark matter, and the two behaved differently. Dark matter, which does not interact with light or radiation, began collapsing into structures earlier than normal gas. It formed vast gravitational halos that served as invisible frameworks for later galaxy formation. Ordinary gas eventually followed, falling into these dark matter wells and forming denser regions where stars could later ignite. Theoretical understanding of gravitational stability did not end with James Jeans. Several decades later, the astrophysicist Subrahmanyan Chandrasekhar expanded and refined many of the mathematical tools used to describe gravitational systems. Chandrasekhar was a brilliant theoretical physicist whose work shaped large areas of astrophysics. He studied the stability of rotating fluids, the equilibrium of stars, and the dynamics of gravitational collapse. One of his most famous contributions was the Chandrasekhar limit, which describes the maximum mass a white dwarf star can possess before collapsing under its own gravity. But his broader work on gravitational stability also helped clarify how self-gravitating systems behave under different physical conditions. Through careful mathematical analysis, Chandrasekhar demonstrated how gravitational collapse depends on factors such as rotation, turbulence, and energy transport within gas clouds. These refinements helped astrophysicists understand how cosmic structures form in environments far more complicated than the idealized models first studied by Jeans. Together, the insights of Jeans and Chandrasekhar laid the groundwork for modern theories of structure formation. Their work revealed that gravitational instability is not merely a curiosity. It is the fundamental engine that transforms a smooth universe into one filled with stars and galaxies. The small density fluctuations created during inflation provided the seeds, but gravity was the force that nurtured those seeds and allowed them to grow. Over hundreds of millions of years, slightly denser regions accumulated more and more matter. Gas clouds collapsed into growing halos of dark matter. These halos merged and expanded, creating deeper gravitational wells capable of capturing even larger quantities of gas. Gradually, the universe transitioned from a nearly uniform state into a richly structured cosmic environment. Gravity had begun its long, patient work. What started as tiny statistical irregularities in the early universe was slowly becoming the framework for the first stars and the first galaxies. The transformation was slow, almost imperceptible on human timescales, yet across cosmic history, gravity's quiet persistence would eventually reshape the universe into the vast and intricate structure we observe today. As the early universe continued expanding and cooling, gravity slowly began drawing matter into the slightly denser regions seeded by quantum fluctuations. Gas drifted inward, dark matter gathered quietly, and the first large structures were beginning to take shape. But as astronomers later studied galaxies in detail, they encountered a mystery that changed our understanding of the cosmos. The visible matter in the universe did not seem to be enough to explain what gravity was doing. The first hints of this puzzle appeared in the 1930s through the work of the Swiss astronomer Fritz Zwicky. Zwicky was studying the Coma Cluster, a massive gathering of galaxies located more than 300 million light-years away. By measuring the speeds at which galaxies moved inside this cluster, he noticed something unusual. The galaxies were moving far too quickly. According to Newton's laws of gravity, objects bound together in a gravitational system must move at speeds determined by the amount of mass present. If the cluster contained only the matter astronomers could see, primarily stars and glowing gas, then the galaxies should have been moving much more slowly. Instead, they were racing around the cluster at enormous velocities. Zwicky realized that the cluster must contain far more mass than telescopes were revealing. To describe this hidden mass, he used the German phrase dunkle Materie, which translates to dark matter. At the time, the idea did not attract widespread attention. Astronomers suspected that perhaps faint stars, cold gas clouds, or other dim objects might account for the missing mass. But over the following decades, new observations made the mystery harder to dismiss. The most compelling evidence arrived in the 1970s through the work of the American astronomer Vera Rubin. Rubin studied the rotation of spiral galaxies by measuring how fast stars moved around their galactic centers. According to classical gravitational theory, stars located far from the center of a galaxy should orbit more slowly than those near the core. This expectation comes from the way gravity behaves in systems dominated by a central mass. The farther an object is from the center, the weaker the gravitational pull it experiences. In simple terms, one would expect the outer parts of a galaxy to rotate more slowly, much like the outer planets in our solar system take longer to orbit the Sun, but Rubin's measurements revealed something very different. Stars at the outer edges of galaxies were moving almost as quickly as stars closer to the center. Their orbital speeds remained nearly constant across large distances. These observations produced what astronomers call flat rotation curves. For these outer stars to move this quickly without flying away into space, galaxies must contain far more mass than the visible stars and gas could account for. The additional mass appeared to form a vast invisible halo surrounding each galaxy. Today, astronomers believe that dark matter outweighs ordinary matter by roughly a factor of 5. While stars, planets, and gas make up the luminous structures we can observe directly, the majority of matter in the universe remains unseen. Dark matter does not emit light, absorb light, or interact strongly with electromagnetic radiation. Its presence is revealed primarily through its gravitational influence. In modern cosmology, dark matter plays a crucial role in the formation of galaxies. Long before stars formed, dark matter began collapsing under its own gravity. Because dark matter does not interact with radiation in the same way as ordinary gas, it was free to begin clumping together earlier in the history of the universe. Over time, it gathered into large structures known as dark matter halos. These halos form the hidden architecture of the cosmos. They act as enormous gravitational wells that pull ordinary gas inward. As gas falls into these halos, it becomes compressed and heated, eventually cooling and forming the first stars. In this way, dark matter provides the gravitational framework upon which galaxies are built. During the late 20th century, cosmologists began constructing detailed theoretical models to understand how dark matter shapes the universe. Among the most influential contributors to this work was the physicist Jim Peebles. Peebles played a central role in developing the modern theory of cosmic structure formation. His research explored how small density fluctuations grow under gravity and how dark matter influences the large-scale distribution of galaxies. Later computational simulations expanded these ideas dramatically. In the 1980s and 1990s, researchers such as Simon White, Carlos Frenk and their collaborators used powerful supercomputers to model the evolution of dark matter across cosmic time. Their simulations revealed that dark matter forms an intricate network of filaments, sheets, and dense nodes that stretch across the observable universe. This vast structure is now known as the cosmic web. At the intersections of these filaments, dark matter accumulates into massive halos. Within those halos, ordinary gas collects and eventually forms galaxies. Smaller halos merge together over time, building larger galaxies through a process known as hierarchical structure formation. In this picture, the visible universe is only the luminous surface of a much larger invisible structure. Galaxies trace the densest regions of the cosmic web, like glowing lanterns hanging from an enormous gravitational scaffold made almost entirely of dark matter. Despite its success, the dark matter hypothesis continues to raise profound questions. Scientists still do not know what dark matter is made of. Many theories suggest that dark matter consists of new types of particles that interact only weakly with ordinary matter. Physicists have proposed candidates such as weakly interacting massive particles, often abbreviated as WIMPs, as well as other hypothetical particles like axions. Large experiments around the world are attempting to detect these particles directly. Facilities such as the Large Hadron Collider at CERN, along with underground detectors located deep beneath mountains and mines, are searching for evidence of dark matter interactions. At the same time, some physicists have explored alternative explanations. One such proposal is known as self-interacting dark matter. This idea was developed in the early 2000s by David Spergel and Paul Steinhardt. In this model, dark matter particles occasionally collide with one another, altering how dark matter behaves inside galaxies. These interactions could potentially explain certain features of galaxy structure that standard dark matter models struggle to reproduce. Another line of thought challenges the existence of dark matter entirely. In 1983, the Israeli physicist Mordechai Milgram proposed a theory known as modified Newtonian dynamics, often abbreviated as MUND. Instead of introducing unseen matter, MUND modifies the laws of gravity at extremely low accelerations. According to this idea, gravity behaves slightly differently on the large scales typical of galaxies, producing the observed rotation curves without requiring dark matter. MUND has had some success in describing the motions of stars within individual galaxies. However, it struggles to explain larger cosmic structures such as galaxy clusters and the cosmic microwave background. As a result, most cosmologists currently favour the dark matter explanation, particularly within the framework known as the lambda cold dark matter model. In this model, cold dark matter forms the gravitational backbone of the universe, while a mysterious form of energy known as dark energy drives the accelerating expansion of space. Yet despite decades of research, dark matter itself remains undetected in laboratory experiments. It is one of the most important unsolved mysteries in modern physics. What we do know is that without dark matter, the universe would likely look very different. The growth of cosmic structure would have been far slower. Gas alone would have struggled to collapse efficiently under gravity. Galaxies might have taken far longer to form, and the vast cosmic web we observe today might never have emerged in its current form. Dark matter, though invisible, appears to have guided the development of cosmic structure from the very beginning. It created the gravitational wells that gathered matter. It shaped the cosmic web that spans the universe, and within its enormous halos, the first galaxies were able to take shape. In many ways, the story of galaxy formation is also the story of dark matter, quietly shaping the universe from behind the scenes. Like an invisible framework supporting an immense cosmic cathedral, dark matter provides the structure upon which the luminous universe is built. As gravity continued its quiet work, the slightly denser regions of the early universe began gathering matter from their surroundings. Dark matter collapsed first, forming enormous halos that would later host galaxies. Gas followed slowly behind, falling inward along gravitational pathways that had been established long before the first stars ever ignited. But the universe did not simply condense into isolated clumps scattered randomly through space. Instead, gravity shaped matter into an extraordinary large-scale pattern. When astronomers eventually mapped the distribution of galaxies across billions of light years, they discovered that the universe has a kind of architecture. Galaxies are not spread evenly through space. Rather, they form enormous interconnected structures that resemble a vast network of threads. This structure is now known as the cosmic web. In the cosmic web, galaxies gather along long filaments of matter, stretching across hundreds of millions of light years. These filaments intersect at dense nodes, where galaxy clusters form. Between them lie immense regions of nearly empty space known as cosmic voids. If one could view the large-scale structure of the universe from far above, the pattern would resemble a sponge or a delicate network of interconnected strands. Vast empty bubbles are surrounded by thin sheets and filaments of matter, with galaxies glowing along these structures like lights along a sprawling cosmic highway. Understanding how this pattern forms required a breakthrough in theoretical cosmology. One of the most influential ideas came from the Soviet physicist Yakov Zeldovich. In the early 1970s, Zeldovich proposed a remarkably elegant model, describing how matter collapses under gravity in an expanding universe. Instead of imagining matter collapsing evenly in all directions at once, Zeldovich realized that gravitational collapse tends to occur unevenly. Regions of slightly higher density do not shrink symmetrically like a contracting sphere. Instead, collapse usually happens first along one direction. Imagine a vast cloud of matter slowly compressing under gravity. The first stage of collapse flattens the cloud into a large sheet. Zeldovich called these structures pancakes, not because they resemble breakfast food exactly, but because the image captures the idea of matter collapsing into thin layers. Once these sheets form, gravity continues working. The material within them collapses further along a second direction, creating long, narrow filaments. Finally, matter within the filaments may collapse along a third direction, forming dense knots where the filaments intersect. This sequence produces a natural hierarchy of structures. First come sheets, then filaments, then dense nodes. These nodes eventually become the birthplaces of galaxy clusters. Zeldovich's insight was profound because it showed that large-scale structure could emerge naturally from gravitational instability, acting on the tiny fluctuations present in the early universe. Gravity does not simply gather matter into isolated blobs. Instead, it organizes matter into interconnected networks. At the time Zeldovich proposed his model, computers were not yet powerful enough to simulate the universe in detail. But as computational technology improved, cosmologists began testing these ideas through large-scale numerical simulations. During the 1980s and 1990s, a group of researchers including Mark Davis, George Efstathiou, Carlos Frenk and Simon White began running some of the first sophisticated simulations of cosmic structure formation. Using powerful supercomputers, they modeled the gravitational evolution of millions of particles representing dark matter across billions of years of cosmic time. The results were striking. As the simulated universe evolved, matter organized itself into patterns almost identical to Zeldovich's predictions. Vast sheets formed first, then stretched into long filaments connecting massive clusters. Between these structures grew enormous empty regions where matter had drained away. These voids could reach tens or even hundreds of millions of light-years across. Meanwhile, the filaments and nodes became increasingly dense as gravity continued pulling material inward. When astronomers later mapped the real universe using large galaxy surveys, such as the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey, they found that the actual distribution of galaxies closely matched the patterns seen in these simulations. The universe truly does resemble a cosmic web. However, Zeldovich's original approximation had one limitation. When matter collapses along a direction, the model predicts that particles can pass through each other, producing unrealistic overlaps in the simulated structures. In reality, matter tends to accumulate into stable filaments, rather than simply flowing through itself indefinitely. To address this issue, cosmologists developed a refinement known as the adhesion model. The adhesion model introduces a small effective viscosity into the equations describing cosmic matter flow. This viscosity does not represent ordinary friction in the usual sense. Instead, it acts as a mathematical tool that prevents matter from crossing through itself once collapse begins. When this effect is included, the simulated structures become sharper and more stable. Filaments remain well defined, and dense nodes form naturally where multiple filaments intersect. In the adhesion model, matter behaves almost like a sticky fluid. Once particles come together along a collapsing structure, they remain bound within it. This approach produces remarkably realistic cosmic networks. Within these filaments and nodes, dark matter halos grow larger through mergers and continued gravitational attraction. Gas falling into these halos becomes compressed and heated, eventually cooling and forming stars. Galaxies therefore emerge along the skeleton of the cosmic web. Many galaxies reside along filaments, drifting slowly along these immense gravitational highways. But the most massive galaxies tend to appear at the intersections where several filaments converge. These intersections are the densest environments in the universe. Clusters of galaxies may contain hundreds or even thousands of individual galaxies bound together by gravity. The combined mass of these clusters, dominated by dark matter, can reach quadrillions of times the mass of the Sun. Between the filaments lie the cosmic voids. Voids are not completely empty, but they contain far fewer galaxies than average regions of space. Their existence arises naturally from gravitational evolution. As matter flows toward filaments and clusters, the regions between them gradually lose material. Over billions of years, these areas expand into enormous cavities. Some of the largest known cosmic voids span more than 300 million light-years. Despite their immense size, these voids are among the quietest environments in the universe, containing only a sparse scattering of galaxies. From a distance, the entire structure resembles a vast sponge or foam filling the cosmos. Filaments stretch like strands of silk across space. Clusters glow at their intersections, and enormous bubbles of emptiness drift between them. This cosmic web represents the large-scale framework of the universe. Galaxies form not randomly, but within this intricate network sculpted by gravity and dark matter. The web itself began as a pattern of tiny density fluctuations in the early universe. Over billions of years, gravitational attraction amplified those fluctuations, guiding matter along preferred directions and assembling the immense structures we observe today. The cosmic web is therefore both a map of the universe and a record of its history. Every filament, every cluster, every vast, empty void traces the patient influence of gravity acting across cosmic time. Within this web, the stage was now set for the next transformation. Gas was gathering in the densest regions. Dark matter halos were growing larger, and inside these gravitational wells the first true galaxies would soon begin to form. As the invisible framework of dark matter spread across the universe, ordinary matter began responding to its gravitational pull. The young cosmos contained vast quantities of gas composed almost entirely of hydrogen and helium. The simplest elements formed during the first few minutes after the Big Bang. These gases filled the expanding universe like a thin cosmic atmosphere. Where dark matter halos had gathered, gravity created deep gravitational wells. Hydrogen and helium drifting through space gradually began falling inward toward these regions. The process unfolded slowly, guided by the same gravitational forces that had already shaped the cosmic web. But gas behaves very differently from dark matter. Dark matter interacts almost exclusively through gravity. It passes through itself without friction and forms structures relatively easily. Ordinary gas, on the other hand, is governed by additional physical processes. Pressure, temperature, radiation, and chemistry all influence how gas moves and collapses. Understanding how the first stars formed therefore requires understanding the physics of gas itself. When hydrogen and helium gas began falling into dark matter halos, it did not immediately collapse into dense objects. As gas falls inward under gravity, it gains kinetic energy and heats up. This heating increases the internal pressure of the gas, pushing outward and resisting further collapse. In other words, gravity tries to compress the gas while pressure pushes back. Whether a cloud collapses further depends largely on its ability to lose heat. If the gas can cool efficiently, its pressure drops and gravity gains the advantage. But if the gas remains hot, pressure continues resisting gravitational compression. This delicate balance between heating and cooling plays a crucial role in determining where stars can form. During the 1960s and 1970s, astrophysicists began exploring this problem in detail. Among the researchers who made important contributions were Martin Rees and Joseph Silk, both of whom studied how gas behaves inside gravitational structures. Joseph Silk, in particular, investigated how interactions between radiation and matter in the early universe could smooth out small density fluctuations. This effect became known as Silk damping. In the young universe, photons of radiation interacted strongly with charged particles such as electrons and protons. As photons scattered repeatedly through this dense plasma, they carried energy from one region to another. This diffusion process effectively blurred out small-scale fluctuations in the density of matter. Silk damping therefore erased the smallest irregularities in the cosmic density field. Only fluctuations larger than a certain scale survived this smoothing effect. These surviving fluctuations would later grow under gravity and eventually give rise to galaxies. In simple terms, silk damping helped determine the smallest structures that could form in the universe. Once the universe cooled enough for atoms to form and radiation decoupled from matter, gas was free to collapse more efficiently. Hydrogen and helium clouds began drifting into dark matter, halos, along the filaments of the cosmic web. Yet another challenge remained. For gas to collapse into the dense objects that eventually produce stars, it must cool dramatically. A collapsing gas cloud can reach temperatures of thousands of degrees. Without a mechanism to radiate this heat away, pressure will halt the collapse before the cloud becomes dense enough to ignite nuclear fusion. In the modern universe, heavy elements such as carbon, oxygen, and silicon provide efficient cooling channels. Atoms of these elements emit radiation as they transition between energy states, allowing gas clouds to shed energy and continue collapsing. But the earliest universe contained none of these elements. At that time, the only available ingredients were hydrogen and helium. These simple atoms are relatively inefficient at cooling gas. As a result, astrophysicists once wondered whether the first stars could form at all. The solution came from a subtle piece of chemistry. Under certain conditions, hydrogen atoms can combine to form a molecule known as molecular hydrogen. This molecule contains two hydrogen atoms bound together. Although molecular hydrogen is extremely rare in the early universe, it plays an outsized role in cooling primordial gas. When molecular hydrogen molecules collide with other particles, they can transition between different rotational and vibrational states. During these transitions, the molecule emits photons, allowing the gas to radiate energy away. This process acts as a cooling mechanism. Even a small fraction of molecular hydrogen within a gas cloud can allow it to lose heat efficiently enough for gravitational collapse to continue. Once cooling begins, the cloud can contract further. As the gas compresses, its density increases, strengthening gravity's grip and accelerating the collapse. Over time, large clouds of hydrogen and helium begin fragmenting into smaller clumps. Each clump may continue collapsing independently, eventually forming the seeds of individual stars. Theoretical models suggest that the first star-forming clouds likely had masses between tens of thousands and several million times the mass of the Sun. Inside these clouds, smaller regions became gravitationally unstable and continued collapsing into dense protostars. The exact details of this process have been studied through sophisticated computer simulations conducted by research groups around the world. Scientists such as Tom Abel, Volker Brom, and Naoki Yoshida have simulated the formation of primordial stars using high-resolution numerical models. These simulations reveal that the earlier star-forming clouds were likely quite different from the molecular clouds seen in modern galaxies. Because cooling was less efficient, the collapsing gas fragments tended to be much larger. As a result, the first stars were probably extremely massive compared with typical stars today. Some theoretical models suggest that early stars may have reached masses hundreds of times greater than the Sun. Gas dynamics therefore played a decisive role in shaping the earlier structures in the universe. Dark matter halos provided the gravitational wells that gathered matter. But the detailed behavior of gas determined whether stars could actually form within those wells. If cooling processes worked efficiently, gas clouds could collapse into dense regions capable of igniting nuclear fusion. If cooling failed, pressure would halt the collapse, and the gas would remain diffuse. The birthplaces of the first stars therefore emerged from the complex interaction between gravity, chemistry, and thermodynamics. Hydrogen and helium drifting through the cosmic web slowly accumulated in dark matter halos. Molecular hydrogen allowed the gas to cool. Cooling allowed collapse to continue, and inside those collapsing clouds, the universe was preparing to ignite its very first stars. What had begun as tiny density fluctuations in the early universe was now becoming something far more dramatic. The first stellar lights were about to appear. As primordial gas continued gathering within dark matter halos, the universe approached a turning point. For hundreds of millions of years after the Big Bang, space had remained dark. Hydrogen and helium filled the expanding cosmos, drifting through the growing cosmic web, but no stars yet existed to illuminate the darkness. Eventually, in the densest regions of collapsing gas clouds, conditions reached a critical threshold. Gravity had compressed the gas to enormous densities. Cooling through molecular hydrogen had allowed the temperature to fall enough for collapse to continue. At the center of these clouds, the pressure and temperature grew steadily higher. When the temperature climbed to many millions of degrees, a remarkable transformation occurred. Hydrogen nuclei began to fuse together, forming helium and releasing enormous amounts of energy. The first stars had ignited. Astronomers refer to these earlier stars as population 3 stars. The name reflects a historical classification system developed during the 20th century. Astronomers studying the Milky Way noticed that some stars contained many heavy elements, while others contained very few. The metal-rich stars, which formed later in cosmic history, were labelled population 1. Older stars with fewer heavy elements became known as population 2. When scientists began thinking about the very first stars, those that formed before any heavy elements existed at all, they naturally called them population 3. These stars were unique because they formed from completely pristine material. Their gas clouds contained only hydrogen, helium, and trace amounts of lithium produced during Big Bang nucleosynthesis. None of the heavier elements such as carbon, oxygen, nitrogen, or iron had yet been created. In astronomy, elements heavier than helium are collectively referred to as metals, even if they are not metallic in the everyday sense. Because population 3 stars formed before any of these elements existed, they are sometimes described as metal-free stars. This seemingly small difference had enormous consequences. Heavy elements are extremely important in regulating the cooling of gas clouds. In modern star-forming regions, atoms such as carbon and oxygen radiate energy efficiently, allowing gas to cool and fragment into many small clumps. This process leads to the formation of stars with a wide range of masses, including many small stars like our Sun. But the primordial gas that formed population 3 stars lacked these cooling channels. As a result, the collapsing clouds were unable to fragment into many small pieces. Instead, they tended to produce only a few very large clumps of gas. These clumps continued collapsing until they formed massive protostars. Over the past few decades, researchers have used advanced computer simulations to study this process in detail. Among the scientists who have made important contributions are Volker Brom, Tom Hubble, and Naoki Yoshida. Their simulations follow the evolution of primordial gas clouds from their initial collapse all the way to the formation of the first stars. By including detailed models of gravity, gas dynamics, and molecular chemistry, these studies provide our best glimpse into a time long before the first galaxies fully assembled. The results suggest that population 3 stars were likely far larger than typical stars today. In many simulations, the first stars grow to masses between tens and several hundreds of times the mass of the Sun. Some models even allow stars approaching 1,000 solar masses under extreme conditions. A star of 100 solar masses shines millions of times brighter than the Sun and burns through its nuclear fuel extremely quickly. While the Sun will live for roughly 10 billion years, such massive stars may survive only a few million years before exhausting their fuel. In cosmic terms, they are brilliant but short-lived. Despite their brief lifetimes, these early stars had a profound impact on the universe. Their intense radiation began transforming the surrounding environment. Ultraviolet light streamed outward from their surfaces, heating and ionizing nearby hydrogen gas. This process gradually began lifting the universe out of its long, dark age. The appearance of these stars marked the beginning of cosmic dawn. Their radiation also influenced the formation of later generations of stars. Strong stellar winds and powerful radiation fields altered the surrounding gas clouds, sometimes triggering new collapses while at other times dispersing gas and delaying star formation. In addition to radiation, the deaths of these massive stars played an equally important role. When a very massive star reaches the end of its life, its core collapses and the star may explode in an enormous supernova. Some population 3 stars may have ended their lives in a particularly powerful type of explosion known as a pair instability supernova. These explosions occur when extremely energetic photons inside the star begin converting their energy into pairs of electrons and positrons. This process destabilizes the star's core, leading to a runaway collapse followed by a catastrophic explosion that can completely tear the star apart. Such explosions release tremendous amounts of energy and scatter newly formed elements into surrounding space. Inside the cores of these first stars, nuclear fusion had created the universe's first heavy elements. Carbon, oxygen, silicon, and iron were forged through successive stages of nuclear burning. When the stars exploded, these elements were dispersed into the surrounding gas. For the first time, the universe contained more than just hydrogen and helium. This chemical enrichment changed everything that came afterward. Gas clouds enriched with heavy elements could cool more efficiently, fragment more easily, and form stars of lower mass. In other words, the first stars prepared the universe for the generations of stars that would follow. While the basic picture of population 3 stars is widely accepted, some theoretical ideas suggest that the earlier stars may have behaved in even more unusual ways. One particularly intriguing concept is the idea of dark stars. This idea was explored by the physicist Catherine Fries and her collaborators during the early 2000s. In this model, the first stars might have been powered not only by nuclear fusion, but also by interactions involving dark matter. The concept relies on the possibility that dark matter particles can annihilate when they encounter each other. In certain theoretical models, when two dark matter particles meet, they may convert their mass into energy. If large amounts of dark matter collected inside the first protostars, the energy released from these annihilations could heat the star's interior. Instead of immediately igniting nuclear fusion, the star might be supported by energy generated from dark matter interactions. Such a dark star would be very different from ordinary stars. It might grow extremely large, perhaps even reaching sizes larger than our entire solar system. Because its energy source would be distributed throughout its interior, its surface temperature might remain relatively cool despite its enormous size. Although dark stars remain hypothetical, the idea highlights how the earliest phases of cosmic evolution may have included exotic phenomena that no longer occur today. Whether powered purely by nuclear fusion or influenced by dark matter interactions, the first stars transformed the young universe in fundamental ways. They illuminated the darkness, they forged the first heavy elements, and through their radiation and explosive deaths, they reshaped the surrounding gas clouds from which future generations of stars and galaxies would emerge. From these beginnings, the universe was becoming steadily more complex. The quiet collapse of primordial gas had ignited the first stellar lights, and those lights were beginning to change everything that followed. The first stars did not live quietly. They were enormous, brilliant, and short-lived. Born from pristine clouds of hydrogen and helium, many of these early stars burned through their nuclear fuel with extraordinary intensity. A star with tens or hundreds of times the mass of the Sun releases energy at a staggering rate. Its core temperatures climb to tens of millions of degrees, allowing nuclear fusion to proceed rapidly. But even the brightest stars cannot shine forever. Eventually, the nuclear fuel within their cores begins to run out. When that happens, gravity once again takes control. Inside a massive star, nuclear fusion produces energy that pushes outward against gravity. This outward pressure keeps the star stable. As long as fusion continues in the core, the star maintains a delicate balance between collapse and expansion. When the fuel is exhausted, that balance fails. Without sufficient outward pressure, gravity begins compressing the star's core. Temperatures and densities rise dramatically. In some cases, this compression triggers additional fusion stages that briefly stabilize the star again. Hydrogen fuses into helium. Helium fuses into carbon. Carbon may fuse into heavier elements such as oxygen, neon, and silicon. But this process cannot continue indefinitely. Eventually, the core begins producing iron. Iron presents a problem for stellar fusion. When lighter elements fuse together, energy is released. But iron sits at the peak of nuclear binding energy. Fusing iron into heavier elements actually requires energy instead of releasing it. Once iron accumulates in the core, fusion can no longer generate the energy needed to resist gravity. The core collapses in a matter of seconds. During this catastrophic collapse, matter compresses to extraordinary densities. The core of a massive star can briefly reach densities comparable to those found inside atomic nuclei. When the collapsing material rebounds against this compressed core, it launches an enormous shockwave outward through the star. The outer layers of the star are violently expelled into space. This event is known as a supernova. A single supernova can briefly shine brighter than an entire galaxy, containing hundreds of billions of stars. The explosion releases vast amounts of energy, often exceeding 10 raised to the power of 44 joules. To put this into perspective, that is roughly the amount of energy our Sun will emit over its entire lifetime. These explosions are among the most powerful events in the universe, yet the energy of the explosion is only part of their importance. Supernovae also perform one of the most remarkable acts of cosmic chemistry. Inside the extreme temperatures and pressures created during the explosion, atomic nuclei collide and fuse in ways that cannot occur under ordinary conditions. This process creates many of the heavier elements found throughout the universe. The idea that stars manufacture elements was not always obvious. For many years, scientists wondered where elements heavier than helium originated. The Big Bang itself could only produce hydrogen, helium, and a small amount of lithium. Yet the Earth and other planets contain a rich assortment of heavier elements such as carbon, oxygen, silicon, calcium, and iron. The solution emerged through the theory of stellar nucleosynthesis. During the 1950s, a group of physicists and astronomers developed a detailed explanation for how stars create elements through nuclear reactions. Among the key contributors were Fred Hoyle, Margaret Burbidge, Geoffrey Burbidge, and William Fowler. Their work was published in a famous paper in 1957, often referred to by astronomers as the B²FH paper, using the initials of the four authors. This research showed how successive stages of nuclear fusion inside stars can build heavier elements from lighter ones. Hydrogen fuses into helium. Helium nuclei combine to form carbon through a reaction known as the triple alpha process. Carbon can fuse with helium to produce oxygen. In increasingly massive stars, additional fusion reactions produce elements such as neon, magnesium, silicon, and eventually iron. However, the production of many elements heavier than iron requires the extreme conditions found in supernova explosions. In the intense environment created by the explosion, rapid neutron capture processes occur. These processes allow atomic nuclei to build up into heavier elements such as gold, platinum, and uranium. In other words, many of the elements that make up planets, mountains, oceans, and even living organisms were forged during the violent deaths of stars. When a supernova explodes, these newly formed elements are hurled outward into space at speeds of thousands of kilometers per second. Expanding shock waves sweep through the surrounding gas, mixing heavy elements into the interstellar medium. Over time, the debris from countless supernovae spreads throughout galaxies. The once pristine hydrogen and helium clouds of the early universe gradually become enriched with heavier elements. Astronomers describe this process as chemical enrichment. The gas between stars slowly accumulates increasing amounts of carbon, oxygen, nitrogen, silicon, and iron. Each generation of stars contributes more material, gradually transforming the chemical composition of the universe. This enrichment has profound consequences for the formation of future stars. Heavy elements are extremely effective at radiating energy away from gas clouds. Atoms such as carbon and oxygen can emit radiation through transitions between electronic energy levels, allowing collapsing gas clouds to cool much more efficiently. Dust grains, which form from heavy elements, also play an important role in cooling gas and shielding molecular clouds from radiation. As cooling improves, gas clouds fragment more easily into smaller clumps. Instead of forming only a few extremely massive stars, enriched gas clouds produce a wide range of stellar masses. This shift marks the transition from the earliest population 3 stars to the later populations that populate galaxies today. In effect, the first generation of stars transformed the cosmic environment in which later generations would form. They acted as cosmic alchemists, turning simple hydrogen and helium into the complex mixture of elements that fills the universe today. Their explosions seeded the gas clouds from which future stars and planets would eventually emerge. Without this chemical transformation, galaxies would look very different. Stars might remain enormous and short-lived. Rocky planets composed of heavy elements might never form. The complex chemistry necessary for life would likely be impossible. Instead, the universe gradually became richer and more diverse. Every supernova scattered new elements across interstellar space. Every generation of stars inherited the chemical legacy of those that came before. Over hundreds of millions of years, this cycle of star formation, nuclear fusion, and explosive death slowly transformed the universe from a simple mixture of hydrogen and helium into a chemically complex environment. Within that enriched gas, galaxies continued assembling along the cosmic web, and with each new generation of stars, the universe became more capable of building the structures we observe today. When the first stars ignited, they did more than simply shine. Their light began altering the physical state of the universe itself. For hundreds of millions of years after the Big Bang, most of the hydrogen filling space existed in a neutral form. Each hydrogen atom consisted of a single proton and a single electron bound together by electromagnetic attraction. In this neutral state, hydrogen atoms can absorb certain wavelengths of light, but do not strongly interact with radiation in many other ways. This quiet, neutral gas filled the expanding universe like an enormous cosmic fog. Then the first luminous sources appeared. The earliest stars, many of them extremely massive, produced enormous quantities of high-energy ultraviolet radiation. This radiation carried enough energy to strip electrons away from hydrogen atoms. When a photon with sufficient energy strikes a hydrogen atom, it can remove the electron from the proton. The atom is no longer neutral. Instead, it becomes an ionized plasma consisting of free protons and free electrons. This process is called ionization. As more and more stars began forming in the early universe, their radiation gradually started ionizing the surrounding hydrogen gas. Regions around young stars became filled with ionized hydrogen, forming expanding bubbles of plasma within the previously neutral universe. Over time, these bubbles grew larger and began overlapping with one another. Eventually, a remarkable transformation occurred. Much of the hydrogen across the universe transitioned from neutral gas back into ionized plasma. Astronomers refer to this dramatic phase of cosmic history as the epoch of reionization. The name may sound slightly confusing at first. The universe had already contained ionized plasma during its earliest moments, before atoms first formed. Later, during the period known as recombination, electrons and protons combined to form neutral atoms. Reionization describes the later process when radiation from stars and galaxies stripped those electrons away once again. This transition fundamentally changed the physical conditions of the cosmos. Understanding when and how reionization occurred has become a major area of research in modern cosmology. Among the scientists who have studied this period in detail are Abraham Loeb and Renan Barkana. Their work has explored how radiation from early galaxies interacted with intergalactic gas and how the first luminous objects influenced their cosmic surroundings. According to theoretical models, reionization likely began a few 100 million years after the Big Bang. The earlier stars produced small ionized regions around themselves. As more stars and early galaxies formed, these ionized bubbles expanded and eventually merged into a vast interconnected network. Within roughly 1 billion years of cosmic history, much of the hydrogen in the universe had become ionized once again. Observations of distant quasars and the absorption features in their light provide important evidence for this transition. Astronomers studying these objects have found that light traveling through the universe begins to encounter large amounts of neutral hydrogen at very high redshifts, corresponding to times before reionization was complete. The gradual disappearance of these neutral regions provides clues about when the universe became fully ionized. The process of reionization was not merely a passive transformation driven by starlight. It also created powerful feedback effects that influenced how galaxies continued forming. When ultraviolet radiation ionizes hydrogen gas, it also heats the surrounding medium. Ionized gas can reach temperatures of tens of thousands of degrees. Hot gas behaves very differently from cold gas. At higher temperatures, gas particles move faster. This increased motion generates stronger pressure, which can prevent gas from collapsing into small dark matter halos. This phenomenon is known as radiative feedback. Radiative feedback occurs when radiation from stars and galaxies alters the surrounding environment in ways that influence future star formation. In the early universe, the heating caused by ionizing radiation made it more difficult for small halos to accumulate gas. In regions flooded with intense ultraviolet radiation, the gas could remain too hot and diffuse to collapse into dense clouds. As a result, some small dark matter halos may have failed to form stars at all. This effect introduced a kind of cosmic competition. Gravity was constantly trying to pull gas into halos and compress it into stars. At the same time, radiation from nearby stars was heating the gas and pushing it away from those same halos. The outcome depended on the balance between these opposing influences. In large halos with stronger gravitational pull, gas could still collapse and form stars despite the heating effects of radiation. In smaller halos, radiative feedback might prevent collapse entirely. This balance played an important role in shaping the early population of galaxies. Regions containing many early stars could produce strong radiation fields that suppress star formation in nearby smaller systems. Meanwhile, more isolated halos might continue forming stars with less interference. The early universe therefore became a patchwork of environments with different conditions for galaxy formation. Some regions experienced rapid bursts of star formation, generating intense radiation and driving powerful feedback effects. Other areas evolved more quietly, gradually building galaxies over longer periods of time. Radiation from early stars also influenced the chemistry of primordial gas. High-energy photons can break apart molecules of molecular hydrogen, which had previously played a crucial role in cooling collapsing gas clouds. Without molecular hydrogen, gas cooling becomes less efficient, making it harder for new stars to form in certain environments. This additional feedback effect further complicated the process of galaxy formation. Instead of a simple story in which gravity steadily gathers matter into stars, the universe now contained multiple competing processes. Gravity pulled gas inward, cooling allowed clouds to collapse, radiation heated gas and sometimes prevented collapse altogether. The formation of galaxies became a dynamic interplay between these forces. In some regions, gravity gained the upper hand and galaxies grew rapidly. In other areas, feedback from nearby stars slowed the process, delaying star formation until conditions changed. Over time, this balance helped shape the distribution of galaxies across the cosmic web. The epoch of rhionization therefore represents more than just a change in the state of hydrogen gas. It marks the moment when stars and galaxies began actively reshaping the universe around them. Their light ionized the cosmic fog, their radiation heated intergalactic space, and their influence created a feedback cycle that regulated the growth of future galaxies. From this point onward, galaxy formation was no longer driven by gravity alone. Instead, it became a complex dance between gravitational attraction, gas cooling, radiation, and stellar explosions. The universe was entering an era where the structures it created could also influence the creation of new structures. And within this evolving cosmic environment, galaxies continued assembling along the vast filaments of the cosmic web. As the universe continued evolving, the invisible structures made of dark matter kept growing. Gravity never stopped working, and the small halos that had first gathered matter in the young cosmos did not remain isolated forever. Instead, they began interacting with one another. Dark matter halos drifted through space along the filaments of the cosmic web. When two halos passed close together, gravity could pull them into a shared orbit. Over time, their mutual attraction would cause them to spiral inward and eventually merge into a larger structure. This process happened again and again across the universe. Small halos combined to form larger ones. Those larger halos later merged with others, producing even more massive systems. Over billions of years, the gravitational assembly of cosmic structure unfolded through a sequence of mergers and gradual growth. Astronomers describe this process as hierarchical structure formation. The word hierarchical refers to the way structures build up step by step. Small components combine to produce larger systems, which themselves merge to form still greater structures. In the context of cosmology, this means that galaxies and galaxy clusters did not appear all at once. Instead, they emerged gradually through the accumulation and merger of smaller dark matter halos. At first, the halos forming in the early universe were relatively modest in mass. Some may have contained only a few million times the mass of the Sun. These early halos gathered gas from their surroundings and hosted the formation of the first stars. But gravity rarely leaves things alone. As halos move through the cosmic web, they collided and merged. When two halos combined, their dark matter mixed together and formed a deeper gravitational well. Gas and stars that had previously belonged to separate systems now found themselves orbiting within the same larger halo. With each merger, the structure grew more massive and more complex. Understanding how this hierarchical process unfolds required new theoretical tools. One of the most influential models was developed in the 1970s by the physicists William Press and Paul Schechter. Their work produced a mathematical framework known as the Press-Schechter formalism. The goal of this formalism was to predict how many dark matter halos of different masses should exist at various times in the history of the universe. Rather than tracking every individual halo, which would be impossible with simple calculations, Press and Schechter used statistical methods to describe the overall distribution of structures. Their approach begins with the idea that the early universe contained small fluctuations in density. As gravity amplifies these fluctuations, some regions eventually become dense enough to collapse into halos. Press and Schechter calculated the probability that a region of space with a given initial density would collapse by a certain time. By combining this probability with the statistical properties of the early density fluctuations, they derived a formula describing how many halos of different masses should exist. In words, the key principle behind the Press-Schechter model can be summarized as follows. The number of halos of a given mass depends on how often the density of matter in the early universe exceeded the threshold required for gravitational collapse. Although the mathematics behind the formalism is intricate, the physical idea is beautifully simple. Regions with larger density fluctuations collapse earlier and form smaller halos. Over time, these halos merge and produce larger structures. The Press-Schechter formalism became a cornerstone of modern cosmology because it allowed researchers to connect the statistical properties of the early universe with the distribution of galaxies observed today. Later studies refined this approach. One important improvement came from Ravi Sheth and Giuseppe Tormen, who developed a more accurate description of halo formation known as the Sheth-Tormen mass function. Their work accounted for the fact that collapsing regions in the universe are not perfectly spherical. In reality, gravitational collapse often occurs along different directions at different rates, producing elongated or irregular structures. By incorporating these effects, the Sheth-Tormen model provided predictions that match numerical simulations more closely. These theoretical tools helped astronomers understand how the population of dark matter halos evolves across cosmic time. But the story becomes even more interesting when we consider what happens to the gas and stars contained within these halos. When two dark matter halos merge, their gravitational fields combine. Gas trapped inside the halos is pulled into new orbits, often producing turbulent flows and shock waves. In some cases, the merging process compresses gas clouds, triggering new bursts of star formation. Stars themselves behave somewhat differently during these events. Unlike gas, which can collide and dissipate energy, stars rarely collide directly. Instead, they respond primarily to gravity. When halos merge, stars from both systems begin orbiting within the newly formed halo, gradually redistributing themselves through a process known as dynamical relaxation. Over time, repeated mergers can transform small star-forming systems into much larger galaxies. These early galaxies are sometimes referred to as proto-galaxies. A proto-galaxy is a young galaxy still assembling its mass through ongoing mergers and gas accretion. It may contain multiple clusters of stars, turbulent gas clouds, and complex gravitational interactions. Unlike the orderly spiral galaxies we see today, proto-galaxies often appear irregular and chaotic. This chaotic phase is a natural consequence of hierarchical growth. Imagine building a large city not by constructing a single massive structure all at once, but by gradually merging smaller towns together over many generations. The result is a landscape shaped by countless mergers and rearrangements. In much the same way, galaxies assembled through repeated collisions and mergers between smaller systems. Over time, these proto-galaxies grew more massive. Some halos accumulated hundreds of millions or even billions of solar masses of dark matter. As their gravitational wells deepened, they attracted larger reservoirs of gas from the surrounding cosmic web. This gas continued fueling star formation, gradually building the stellar populations of young galaxies. At the same time, the halos themselves kept growing through mergers. A halo that began as a small system hosting a few clusters of stars might eventually merge with many others, producing a massive galaxy containing billions of stars. The process also helped establish the larger-scale organization of the universe. Clusters of galaxies formed where many halos merged together along the densest nodes of the cosmic web. These clusters can contain hundreds or even thousands of galaxies bound together by gravity. Meanwhile, filaments continued funneling gas and smaller halos toward these massive structures, feeding their growth over billions of years. Hierarchical structure formation therefore provides a natural explanation for the complex cosmic landscape we observe today. Small structures formed first. Larger systems emerged later through mergers, and over immense stretches of time, the gravitational assembly of halos produced the galaxies and galaxy clusters that populate the universe. The growth of dark matter halos served as the scaffolding for this entire process. Within those halos, gas cooled and condensed. Stars ignited. Proto-galaxies collided and merged, and slowly the first true galaxies began taking shape within the vast gravitational architecture of the cosmic web. As dark matter halos continued merging and growing, many of them began hosting increasingly active regions of star formation. Gas falling into these halos cooled, condensed, and ignited new generations of stars. The systems that formed in this stage of cosmic history were not yet the large, well-organized galaxies familiar to us today. Instead, they were smaller, chaotic, and constantly evolving. Astronomers refer to these early systems as proto-galaxies. A proto-galaxy is essentially a young galaxy still assembling itself. It is a gravitational structure in which stars, gas, and dark matter are actively interacting, but the system has not yet settled into the stable forms we recognize in modern galaxies. These early objects may contain only a few million, or perhaps a few billion stars, far fewer than the hundreds of billions found in galaxies like the Milky Way. They are also much more turbulent environments. Gas clouds within proto-galaxies move rapidly through their dark matter halos, colliding, cooling, and fragmenting. Bursts of star formation occur as dense gas clouds collapse under gravity. Massive young stars produce intense radiation and powerful stellar winds, injecting energy back into the surrounding gas. The result is an environment that is constantly changing. Stars are forming, exploding, and reshaping their surroundings. Gas is flowing inward from the cosmic web while other gas is blown outward by supernova explosions. Dark matter provides the gravitational framework holding the system together, but the visible components remain highly dynamic. Understanding how these early systems evolve into mature galaxies has been a major focus of modern astrophysics. During the 20th century, astronomers such as Sandra Faber and Jeremiah Ostraker played important roles in developing our understanding of galaxy structure and evolution. Sandra Faber's research helped clarify the relationships between the brightness, velocity, and mass of galaxies. Through careful observations, she contributed to the discovery of scaling relations that reveal how stars move inside galaxies and how those motions reflect the gravitational influence of both visible matter and dark matter. Jeremiah Ostraker made major contributions to the theoretical understanding of galaxy formation. His work helped demonstrate that galaxies are embedded within massive halos of dark matter. This insight reinforced the idea that dark matter is essential for explaining how galaxies form and remain gravitationally stable. Together with other researchers, their work helped shape the modern picture of galaxy formation as a process involving both visible and invisible components. When astronomers observe extremely distant galaxies, they're essentially looking back in time. Because light travels at a finite speed, observing galaxies billions of light years away allows us to see them as they appeared billions of years ago. Images captured by telescopes such as the Hubble Space Telescope have revealed that many early galaxies appear very different from the elegant spirals and smooth elliptical galaxies seen in the nearby universe. Instead of well-defined shapes, early galaxies often look irregular, clumpy, and distorted. Some appear as scattered collections of bright star-forming regions. Others show elongated shapes or multiple bright cores, suggesting that they may be in the process of merging with neighboring systems. These observations match the predictions of hierarchical structure formation. If galaxies grow through repeated mergers and gas accretion, then the earliest galaxies should appear messy and unsettled. Their shapes reflect the constant gravitational interactions occurring during their assembly. The gas inside proto-galaxies is particularly turbulent. As gas falls into dark matter halos, it often collides with other streams of gas arriving from different directions along cosmic filaments. These collisions create shock waves that compress the gas and trigger new episodes of star formation. At the same time, radiation and stellar winds from newly formed stars push outward against surrounding gas clouds. When massive stars explode as supernovae, they drive expanding shells of hot gas that can sweep through entire regions of a young galaxy. These energetic processes create a cycle of star formation and feedback. Gas collapses into stars, stars release radiation and explosive energy. That energy disrupts nearby gas clouds. Eventually the gas cools and collapses again, forming another generation of stars. This cycle continues again and again as the proto-galaxy grows. Dark matter remains a silent but essential participant in this process. While stars and gas move dynamically within the galaxy, the surrounding dark matter halo provides the gravitational anchor that holds everything together. Without the halo's gravitational pull, The energetic activity inside proto-galaxies could easily disperse their gas into intergalactic space. Instead, the halo ensures that much of the material remains bound to the system, allowing star formation to continue over long periods of time. As proto-galaxies grow larger, their internal motions gradually become more organized. Repeated mergers mix stars together and redistribute their orbits through gravitational interactions. Gas clouds begin settling into rotating structures, particularly if the system acquires a net angular momentum through tidal interactions with nearby halos. Over hundreds of millions of years, these processes begin shaping proto-galaxies into recognizable forms. Some systems develop rotating disks of gas and stars that will eventually become spiral galaxies. Others experience frequent mergers that disrupt disk formation, producing more rounded systems that may later evolve into elliptical galaxies. The path a proto-galaxy follows depends on many factors. The mass of its dark matter halo plays an important role. Larger halos can retain more gas and support longer periods of star formation. The rate at which the halo merges with neighboring systems also influences the galaxy's final structure. Frequent mergers tend to produce more chaotic and spheroidal galaxies, while quieter environments allow rotating disks to develop. Gas accretion from the cosmic web provides another important ingredient. Filaments of gas can deliver fresh material into proto-galaxies, sustaining star formation for extended periods. In some cases, these inflows of gas create rotating streams that help build the large galactic disks seen in spiral galaxies. Over time, the repeated cycles of gas inflow, star formation, and gravitational mergers gradually transform proto-galaxies into mature galactic systems. What began as a small, turbulent cloud of gas inside a dark matter halo can grow into a massive galaxy containing billions of stars. Along the way, the galaxy develops structure. Rotating disks form, central bulges emerge, clusters of stars populate the surrounding halo. The chaotic environment of early cosmic history slowly settles into more stable arrangements. Yet traces of that early turbulence remain visible. Even in modern galaxies, astronomers can observe evidence of past mergers, streams of stars left behind by disrupted satellite galaxies, and vast halos of dark matter extending far beyond the visible disk. These features remind us that galaxies are not static objects. They are living systems shaped by billions of years of gravitational interactions, gas dynamics, and stellar evolution. The proto-galaxies of the early universe were the first chapters in this long and complex story. From their turbulent beginnings emerged the diverse population of galaxies that fill the cosmos today. One of the most striking features of many galaxies is that they rotate. If you observe a spiral galaxy such as the Milky Way, you will find that its stars orbit around the galactic center in vast, sweeping paths. Billions of stars circle the center together, forming the rotating disk that gives spiral galaxies their graceful shape. This raises an interesting question. Where did that rotation come from? The early universe began with matter distributed in nearly random fluctuations. Gas clouds collapsed under gravity, dark matter halos formed, and proto-galaxies began assembling through mergers and gas accretion. But gravity by itself tends to pull matter inward rather than set it spinning. Yet rotation is everywhere in astronomy. Planets rotate, stars spin, galaxies turn slowly across cosmic time. Understanding the origin of this motion required scientists to consider how gravitational interactions can generate angular momentum. Angular momentum is a fundamental physical quantity that describes rotational motion. In everyday terms, it represents how much spin an object has and how that spin is distributed. In physics, angular momentum depends on both mass and motion. A large object moving around a central point carries more angular momentum than a smaller object moving slowly. One important feature of angular momentum is that it is conserved. In a closed system, the total angular momentum remains constant unless external forces act upon it. This principle explains many familiar phenomena. A spinning ice skater who pulls their arms inward rotates faster, because their angular momentum remains constant while their moment of inertia decreases. In the formation of galaxies, angular momentum emerges through gravitational interactions between neighboring structures. During the 1960s and 70s, cosmologists including Jim Peebles and Richard Gott explored how these interactions might generate rotational motion in collapsing matter. Their work helped establish a theory known as tidal torque theory. The basic idea is that proto-galaxies rarely form in complete isolation. Instead, They exist within the complex gravitational environment of the cosmic web, surrounded by other growing halos and density fluctuations. When a region of matter begins collapsing under gravity, nearby structures exert gravitational forces that are slightly uneven. These uneven gravitational pulls create tidal forces. Tidal forces occur whenever gravity varies across an object. The side of the object closer to the gravitational source experiences a stronger pull than the far side. This difference in force can stretch or twist the object. In everyday life, tidal forces from the Moon create ocean tides on Earth. On cosmic scales, tidal forces between neighbouring halos can twist collapsing clouds of matter. Imagine a large cloud of gas and dark matter beginning to contract under its own gravity. Nearby structures exert gravitational pulls that are not perfectly aligned with the cloud's centre of mass. This misalignment creates a torque, which is a force that produces rotation. Over time, these torques gradually spin up the collapsing region. Even a small gravitational twist applied over millions of years can impart significant angular momentum to a forming galaxy. This process occurs early in the collapse of dark matter halos, long before the galaxy becomes fully assembled. As a result, many halos acquire rotational motion that later influences how gas settles within them. The mathematics describing this process can be expressed through the relationship between torque and angular momentum. In words, the key relationship is the following. The rate of change of angular momentum equals the torque applied to a system. This principle means that gravitational torques acting on a collapsing halo gradually build up its angular momentum. Once a halo has acquired this spin, the gas inside it begins responding to the rotational motion. As gas falls inward toward the centre of the halo, conservation of angular momentum becomes important. Gas that moves closer to the centre must rotate faster, much like a skater spinning more quickly when pulling their arms inward. But gas also behaves differently from stars or dark matter particles. Gas can collide with itself. These collisions cause gas clouds to lose energy through radiation and friction. As a result, gas gradually settles into a rotating structure that minimizes its energy while conserving angular momentum. The most stable configuration for rotating gas is a flattened disk. This is why many galaxies form thin rotating disks rather than spherical clouds of stars and gas. As gas settles into the disk, new stars begin forming within it. These stars inherit the rotational motion of the gas from which they formed, creating the rotating stellar disks observed in spiral galaxies. Over time, the disk becomes populated with billions of stars moving in roughly circular orbits around the galactic center. The amount of angular momentum a galaxy possesses has a profound effect on its appearance. Galaxies with large amounts of angular momentum tend to develop wide, extended disks. These disks can host spiral structures and long-lived star-forming regions. Galaxies with relatively little angular momentum may form more compact and rounded systems. If mergers disrupt the disk, or if angular momentum is redistributed during collisions, the galaxy may evolve into an elliptical shape rather than a spiral. In this way, angular momentum helps determine galaxy morphology. The word morphology simply refers to the shape and structure of galaxies. Spiral galaxies, elliptical galaxies, and irregular galaxies each reflect different histories of angular momentum, gas accretion, and gravitational interaction. Rotation also plays a role in stabilizing galactic disks. Without rotation, gravity would pull gas directly toward the center of the galaxy, producing a dense spherical object. But rotational motion creates centrifugal support that balances the inward pull of gravity. Stars and gas therefore orbit the galactic center rather than collapsing directly into it. The result is the elegant rotating disk structure seen in many galaxies. Within these disks, additional processes begin shaping the galaxy's appearance. Density waves may propagate through the disk, organizing stars and gas into spiral arms. Star formation occurs preferentially along these arms where gas becomes compressed. Meanwhile, the central regions of galaxies may develop bulges containing older stars moving in more complex orbits. Yet beneath all these details lies the same fundamental origin: the slow, gravitational twisting of collapsing matter during the earlier stages of galaxy formation. What began as tiny tidal torques acting on dark matter, halos eventually produced the rotating galaxies that populate the universe today. Across billions of years, those early twists became the graceful rotations of spiral galaxies, the motion of countless stars orbiting together through space, and the quiet turning of galaxies across the vast stage of the cosmos. As gas continues flowing into a growing galaxy, its motion becomes increasingly organized by rotation. The dark matter halo surrounding the galaxy already carries angular momentum acquired through tidal torques during the earlier stages of collapse. Gas falling into this rotating halo does not plunge straight toward the center. Instead, it begins orbiting. This orbiting motion has an important consequence. When gas clouds collide with one another, they lose energy through radiation and friction. These collisions allow the gas to settle gradually into a more stable configuration. While energy can be lost in this way, angular momentum is conserved. The gas cannot simply stop rotating. Because of this constraint, the gas naturally spreads into a flattened structure. Imagine a cloud of material spinning slowly while gravity pulls it inward. Gas particles moving above or below the central plane collide with others and lose vertical motion. Over time, these interactions damp out motion perpendicular to the rotation axis. The remaining motion is primarily around the center, producing a thin rotating disk. This process leads to the formation of what astronomers call a galactic disk. Within this disk, billions of stars form from cooling gas clouds. The stars inherit the rotational motion of the gas from which they formed, so the entire stellar population begins orbiting the galactic center in roughly circular paths. The result is a rotating disk of stars and gas that may span tens of thousands of light years. In galaxies like the Milky Way, this disk contains most of the galaxy's visible mass. The disk itself is remarkably thin compared with its diameter. While the Milky Way stretches about 100,000 light-years across, the thickness of its stellar disk is only a few thousand light-years. Once the disk forms, its internal dynamics become increasingly important. A rotating disk of stars and gas is not perfectly stable. Gravity continues acting within the disk, attempting to pull matter into denser regions. At the same time, the random motions of stars and gas provide pressure that resists collapse. Understanding this balance between gravity and internal motion became a major problem in galactic dynamics. One of the key advances in this field came from the astrophysicist Alaa Toumri. During the 1960s, Toumri studied how rotating disks respond to small disturbances. He developed a mathematical condition that predicts whether a disk will remain stable or fragment into dense clumps. This condition is now known as the Toumri stability criterion. The Toumri criterion compares the gravitational pull trying to collapse a region of the disk with the stabilizing effects of rotation and random motion. In words, the principle can be summarized as follows. A rotating disk becomes unstable and fragments when the gravitational attraction between particles exceeds the stabilizing effects of rotation and internal motion. Toumri expressed this balance through a parameter often called the Q parameter. When the value of this parameter falls below a certain threshold, gravitational instability sets in and the disk begins forming dense structures. In regions where the disk becomes unstable, gas clouds collapse into star-forming regions. This process helps explain why star formation often occurs in clusters or along certain structures within galaxies, yet the disk does not collapse entirely into isolated clumps. Instead, large-scale patterns often emerge within the rotating disk. One of the most beautiful and recognizable of these patterns is the spiral structure seen in many galaxies. For a long time, astronomers struggled to understand why spiral arms exist. If spiral arms were simply groups of stars moving together, the arms should quickly wind up and disappear due to differential rotation. Stars closer to the galactic center orbit faster than those farther out. Over time, this difference in speed would twist any fixed structure into a tightly wound spiral. Observations show that spiral arms persist for much longer than this simple picture would allow. In the 1960s, astrophysicists Chiao Lin and Frank Xu proposed an elegant solution known as density wave theory. According to this theory, spiral arms are not fixed groups of stars moving together through space. Instead, they are regions where the density of stars and gas is temporarily enhanced as material passes through. A useful analogy is a traffic jam on a busy highway. Cars enter and leave the traffic jam continuously. The individual cars move forward, but the traffic jam itself can remain in roughly the same location for an extended period. Spiral arms behave in a similar way. Stars and gas orbit the galaxy and pass through the spiral arms. As they enter these regions of higher density, gas clouds become compressed. This compression can trigger star formation, producing bright young stars that illuminate the arms. Once the stars move out of the dense region, The spiral pattern remains as new material continues passing through. Density wave theory therefore explains how spiral arms can persist even though the stars themselves are constantly moving. Toumri later explored additional mechanisms that can strengthen spiral patterns. One of these mechanisms is known as swing amplification. Swing amplification occurs when small disturbances in a rotating disk are stretched and amplified by differential rotation. As the disturbance rotates through the disk, gravity can temporarily enhance the density of the region, creating a spiral pattern. This process can transform minor irregularities into prominent spiral arms. Swing amplification works particularly well in disks where the balance between gravity and rotation lies near the threshold of instability, described by the Toumri criterion. Together, density wave theory and swing amplification provide powerful explanations for the structure of spiral galaxies. The rotating disk serves as the stage, gravity, rotation, and gas dynamics provide the actors, and the resulting patterns produce the magnificent spiral structures visible in many galaxies. Within these spiral arms, gas clouds collapse to form new generations of stars. Massive young stars illuminate the arms with bright blue light, while older stars continue orbiting quietly through the disk. Over time, the disk evolves as stars form, gas flows inward, and gravitational interactions reshape the structure. Yet the fundamental origin of the disk remains the same. Gas falling into a rotating dark matter halo settles into a flattened plane. Angular momentum organizes the motion of stars and gas. Gravitational instabilities shape patterns within the disk. From these processes emerge the spiral galaxies that decorate the universe with their graceful rotating forms. At the center of most galaxies lies something both mysterious and powerful. Hidden deep within the gravitational heart of these systems are objects so dense that not even light can escape their pull. These objects are known as supermassive black holes. Unlike the black holes formed by the collapse of individual stars, supermassive black holes contain millions or even billions of times the mass of the Sun. The black hole at the center of the Milky Way, known as Sagittarius, a star, has a mass of roughly 4 million solar masses. In some giant galaxies, the central black hole may contain several billion times the mass of the Sun. Despite their name, these black holes are extremely compact. The event horizon of a black hole with a mass of 1 billion suns would be only a few billion kilometers across. In cosmic terms, that is astonishingly small compared with the size of the surrounding galaxy. Yet these compact objects exert a profound influence on the evolution of galaxies. The existence of supermassive black holes in galactic centers was once a matter of speculation. Today, strong observational evidence supports their presence. Astronomers studying the motion of stars near the centers of galaxies have found that these stars orbit extremely massive and compact objects. In the Milky Way, detailed observations using infrared telescopes have tracked the orbits of individual stars near the galactic center. These stars move at enormous speeds as they circle an unseen mass located within a region smaller than our solar system. The simplest explanation for this concentration of mass is a supermassive black hole. The question then becomes how such enormous black holes formed in the first place. One influential line of thought was explored by the astrophysicist Martin Rees. Rees proposed that black holes could have formed early in the universe and grown over time through the accumulation of gas and stars. In one scenario, the first black holes formed from the collapse of extremely massive population 3 stars. When such stars exhausted their nuclear fuel, their cores could collapse directly into black holes containing tens or hundreds of solar masses. These small black holes could then grow by accreting gas from their surroundings. Accretion occurs when gas falls toward a black hole and forms a rotating disk known as an accretion disk. Friction and gravitational forces within the disk heat the gas to extremely high temperatures, causing it to emit intense radiation. As matter spirals inward, it gradually feeds the black hole, allowing its mass to increase. Over millions or billions of years, repeated accretion and mergers with other black holes could transform these small seeds into the supermassive black holes observed today. However, this gradual growth model may not fully explain all observations. Astronomers have discovered quasars, extremely luminous objects powered by rapidly accreting black holes that existed less than 1 billion years after the Big Bang. Some of these quasars appear to contain black holes with masses exceeding 1 billion suns. Growing a black hole to that size within such a short time presents a significant challenge. This puzzle has led scientists to explore alternative models of early black hole formation. One intriguing possibility involves direct collapse black holes. In this scenario, enormous clouds of primordial gas collapse directly into black holes without first forming stars. Instead of fragmenting into many smaller stars, the gas cloud remains relatively smooth and collapses rapidly toward its center. If the gas density becomes high enough, gravity can overwhelm pressure support and produce a black hole containing tens of thousands or even hundreds of thousands of solar masses. This idea has been studied in detail by researchers, including Priyamvada Natarajan and her collaborators. Their work explores the conditions under which direct collapse might occur in the early universe. Such black holes would provide a much larger starting point for later growth, helping to explain how supermassive black holes appeared so early in cosmic history. Regardless of how they formed, one remarkable discovery revealed that supermassive black holes are closely connected to the galaxies surrounding them. Around the turn of the 21st century, astronomers Laura Ferraris and David Merritt independently identified a surprising relationship between the mass of a galaxy's central black hole and the motions of stars in the galaxy's central region. This relationship is known as the M-sigma relation. The symbol sigma refers to the velocity dispersion of stars within the galaxy's central bulge. Velocity dispersion measures how fast stars move in different directions around the galactic center. Ferraris and Merritt found that galaxies with faster-moving central stars tend to contain more massive black holes. In other words, the mass of the central black hole is closely linked to the properties of the galaxy itself. This discovery suggests that black holes and galaxies grow together over cosmic time. The connection becomes clearer when considering the enormous energy released by accreting black holes. As gas falls toward a black hole and forms an accretion disk, gravitational energy is converted into radiation. The energy released in this process can be extraordinary. In fact, the efficiency of energy production near a black hole can exceed that of nuclear fusion inside stars. A small amount of matter falling into a black hole can release enormous energy in the form of radiation and high-speed jets of particles. This energy does not remain confined to the immediate vicinity of the black hole. Powerful outflows of radiation and particles can travel far into the surrounding galaxy. These outflows heat nearby gas, push it outward, and sometimes expel it entirely from the central regions. This process is known as black hole feedback. Black hole feedback can strongly influence the rate at which new stars form within a galaxy. If gas near the galactic center becomes too hot or is blown away by energetic outflows, it can no longer collapse to form new stars. In this way, the black hole effectively regulates the supply of star-forming material. Some galaxies show dramatic evidence of this phenomenon. Observations of active galactic nuclei reveal enormous jets of particles extending thousands of light-years into space. These jets can inflate huge bubbles of hot gas in the surrounding environment, preventing additional gas from cooling and collapsing. In massive galaxies and galaxy clusters, this feedback mechanism may play a crucial role in preventing excessive star formation. The interaction between black holes and galaxies therefore forms a complex feedback loop. Gas falling into the galaxy fuels star formation and feeds the central black hole. The growing black hole releases energy that heats or expels gas. This energy slows or halts further star formation. The result is a delicate balance between growth and regulation. Rather than being passive objects hidden in galactic centers, supermassive black holes actively participate in shaping the evolution of their host galaxies. Their gravity anchors the central regions of galaxies. Their energy output influences the surrounding gas, and their growth appears intimately connected with the development of galactic structure itself. The quiet gravitational collapse that began the story of galaxy formation eventually gave rise to these extraordinary engines of cosmic energy. At the heart of many galaxies, including our own, a supermassive black hole continues to shape the galaxy's evolution from deep within its gravitational well. In the early universe, galaxies were rarely isolated. The cosmic web brought matter together along filaments that stretched across enormous distances, and the dark matter halos embedded within these filaments were constantly moving under the influence of gravity. As a result, galaxies frequently encountered one another. When two galaxies drift close enough, their mutual gravitational attraction begins altering their paths. What might start as a distant flyby can gradually turn into a slow dance lasting hundreds of millions of years. Eventually, the two galaxies merge. These mergers were especially common during the early epochs of cosmic history. At that time, the universe was smaller and denser than it is today. Galaxies were closer together, and the hierarchical growth of dark matter halos continually brought systems into contact. Because of this environment, collisions and mergers played a central role in shaping galactic evolution. Despite the word collision, galaxies do not typically smash together like solid objects. Stars inside galaxies are separated by vast distances. If two galaxies pass through one another, the probability that individual stars will collide is extremely small. Instead, the main interactions occur through gravity. As galaxies approach one another, tidal forces begin distorting their shapes. Long streams of stars and gas may be pulled outward, forming structures known as tidal tails. These tails can stretch for hundreds of thousands of light years into space, tracing the gravitational interaction between the merging systems. Meanwhile, the dark matter halos surrounding the galaxies begin overlapping and mixing. Over time, orbital energy is lost through a process called dynamical friction. This effect occurs when moving objects such as galaxies or dark matter clumps gravitationally disturb surrounding matter. The disturbances create wakes of increased density behind the moving object, which exert a gravitational pull that gradually slows it down. As a result, the two galaxies spiral closer together. Eventually, their cores merge into a single system. During this process, the internal structure of the galaxies can change dramatically. Stars that once orbited in orderly disks may find their paths altered by complex gravitational interactions. Gas clouds collide and compress, often triggering intense bursts of star formation known as starbursts. Massive stars born in these bursts shine brilliantly for a short time before ending their lives in supernova explosions. The result is a galaxy that may look very different from either of its original components. Understanding how galaxies settle into new equilibrium states after such mergers required careful theoretical study. One of the most influential ideas came from the astrophysicist Donald Lynden Bell. In 1967, Lynden Bell introduced a concept known as violent relaxation. Despite its dramatic name, violent relaxation does not refer to an explosion or a sudden catastrophe. Instead, it describes how the orbits of stars rapidly reorganize when the gravitational potential of a system changes quickly. During a galaxy merger, the overall gravitational field fluctuates as the two galaxies interact. Stars moving through this changing gravitational environment experience shifts in their energy and momentum. Their orbits are redistributed across a wide range of trajectories. Over time, this redistribution leads the system toward a new equilibrium configuration. Violent relaxation helps explain how galaxies can transform from one structural type into another following a merger. For example, when two spiral galaxies of similar mass collide, their rotating disks may become disrupted. The orderly circular orbits of stars are replaced by more randomized motions. After the merger settles, the resulting system often resembles an elliptical galaxy. Elliptical galaxies differ from spiral galaxies in several important ways. Instead of a thin rotating disk, elliptical galaxies contain stars moving along many different directions. Their shapes are more rounded or elongated rather than flat. They also tend to contain older stellar populations and relatively little cold gas. Mergers can therefore convert spiral galaxies into ellipticals by redistributing the motions of their stars. Modern astrophysicists have studied these processes using detailed numerical simulations. Among the researchers who made important contributions to this field are Joshua Barnes and Lars Hernquist. During the 1980s and 1990s, they developed sophisticated computer simulations that modeled galaxy collisions with remarkable realism. Their simulations showed how tidal forces stretch galaxies into long tails of stars and gas. They also demonstrated how gas flowing toward the center of the merging system can trigger intense bursts of star formation. One famous example often used to illustrate galaxy mergers is the Antennae galaxies, located about 45 million light-years from Earth. Observations reveal two interacting spiral galaxies with spectacular tidal tails extending far into space. Simulations similar to those developed by Barnes and Hernquist reproduce these features remarkably well, confirming that gravitational interactions can produce the dramatic structures seen in merging galaxies. Mergers do not always produce elliptical galaxies, however. If one galaxy is significantly smaller than the other, the larger galaxy may survive the interaction with its disk mostly intact. The smaller galaxy becomes a satellite that is gradually absorbed into the larger system. These events are sometimes called minor mergers. Minor mergers can add stars, gas, and dark matter to the larger galaxy without completely disrupting its structure. Over time, repeated minor mergers may build up the outer halo of a galaxy and contribute to the growth of its stellar disk. Astronomers have observed many examples of this process in the Milky Way itself. Streams of stars surrounding our galaxy appear to be remnants of smaller galaxies that were torn apart by gravitational interactions and absorbed into the Milky Way over billions of years. This gradual accretion process contributes to the ongoing evolution of galaxies. Repeated mergers, both major and minor, help explain how the largest galaxies in the universe formed. In dense regions such as galaxy clusters, central galaxies may grow to enormous sizes by absorbing many smaller systems. Some of these giant galaxies contain trillions of stars and extend across hundreds of thousands of light years. Their growth is the cumulative result of countless mergers over cosmic time. Through these interactions, galaxies continue evolving long after their initial formation. Gas flows, star formation, gravitational encounters, and the influence of dark matter all combine to reshape galactic structures. The universe, in this sense, behaves less like a static collection of objects and more like a constantly evolving ecosystem. Galaxies are not permanent structures frozen in time. They grow, they interact, they collide and merge. And through these interactions, the cosmic landscape gradually transforms. The galaxies we see today are the result of billions of years of gravitational encounters woven together across the vast tapestry of the cosmic web. The first galaxies formed billions of years ago, long before the Earth existed, long before our Sun ignited, and long before the Milky Way settled into the structure we see today. Yet despite this immense distance in time, astronomers have found ways to observe these ancient systems. Looking deeper into space means looking further back in time. Light travels at a finite speed, roughly 300,000 kilometers each second. Even at this tremendous speed, light requires years to cross interstellar distances and billions of years to cross the observable universe. When we observe a galaxy that lies 10 billion light-years away, the light entering our telescopes began its journey 10 billion years ago. In this sense, powerful telescopes function like time machines. One of the most important instruments for studying distant galaxies has been the Hubble Space Telescope. Launched in 1990, Hubble operates above Earth's atmosphere, allowing it to capture incredibly sharp images of faint and distant objects. Over the decades, Hubble conducted several deep-field surveys where the telescope stared at small, seemingly empty patches of sky for many hours. These observations revealed thousands of extremely distant galaxies, some dating back to only a few 100 million years after the Big Bang. The images showed that many early galaxies appear very different from nearby ones. Instead of well-organized spirals or smooth elliptical shapes, many distant galaxies look irregular and clumpy. Their structures often reflect the turbulent processes that dominated the early universe, including rapid star formation and frequent mergers. More recently, a new generation of instruments has expanded our ability to explore the distant cosmos. The James Webb Space Telescope, launched in 2021, was designed specifically to study the earliest phases of galaxy formation. Unlike Hubble, which observes primarily in visible and ultraviolet light, the James Webb Telescope focuses on infrared wavelengths. This capability is essential for studying very distant galaxies. As the universe expands, light traveling through space becomes stretched to longer wavelengths. This process is known as cosmological redshift. Light that originally left a galaxy as ultraviolet or visible radiation may arrive at Earth billions of years later as infrared light. By observing in the infrared, the James Webb Telescope can detect some of the most distant galaxies ever observed. Within its first years of operation, the telescope has already identified galaxies that appear to have formed only a few 100 million years after the Big Bang. These observations are providing new insights into how quickly the first galaxies assembled and how rapidly stars began forming in the early universe. Ground-based observatories also play an important role in studying distant galaxies. One of the most powerful facilities is the Very Large Telescope, operated by the European Southern Observatory in the Atacama Desert of northern Chile. This observatory consists of multiple large telescopes that can work together using a technique known as interferometry. By combining light from several telescopes, astronomers can achieve extremely high-resolution observations. The dry, clear atmosphere of the Atacama Desert makes it one of the best locations on Earth for astronomical observations. Using instruments like the Very Large Telescope, astronomers can measure the redshift of distant galaxies, determine their chemical composition, and study the motions of stars and gas within them. Sometimes nature itself provides additional help in observing extremely distant galaxies. A phenomenon known as gravitational lensing allows massive objects to act like natural telescopes. This effect was first proposed by the astronomer Fritz Zwicky in the 1930s. Zwicky realized that massive clusters of galaxies could bend the path of light traveling near them due to the gravitational curvature of space. When light from a distant galaxy passes near a massive cluster, the cluster's gravity can distort and magnify the light. The result may appear as stretched arcs, multiple images of the same galaxy, or magnified views of otherwise invisible objects. Astronomers now routinely use gravitational lensing to study extremely distant galaxies that would otherwise be too faint to detect. By combining powerful telescopes with gravitational lensing, researchers have been able to observe galaxies that formed when the universe was only a few 100 million years old. Despite these advances, many questions about galaxy formation remain unanswered. One puzzle is known as the missing satellites problem. Computer simulations based on dark matter models predict that galaxies like the Milky Way should be surrounded by hundreds or even thousands of smaller satellite galaxies. Yet when astronomers observe the Milky Way and nearby galaxies, they find far fewer satellite galaxies than expected. Several possible explanations have been proposed. One idea is that many small dark matter halos never formed stars because radiation and supernova explosions prevented gas from cooling and collapsing. These halos would therefore remain invisible, containing dark matter but little or no luminous material. Another challenge is known as the core cusp problem. Simulations of dark matter halos often predict that the density of dark matter should increase sharply toward the center of the halo, forming what is known as a cusp. However, observations of some dwarf galaxies suggest that their dark matter distribution is flatter near the center, forming what astronomers call a core. This discrepancy has prompted scientists to explore new ideas about the nature of dark matter. One intriguing possibility is known as fuzzy dark matter. In this model, dark matter consists of extremely light particles with wave-like properties on astronomical scales. These particles would behave somewhat differently from the cold dark matter particles typically assumed in standard cosmological models. The physicist Lam Hui and his collaborators have explored how fuzzy dark matter could alter the structure of dark matter halos. The wave properties of these particles might smooth out the central density of halos, potentially resolving the core cusp problem. Whether fuzzy dark matter or another alternative explanation will ultimately prove correct remains an open question. Such puzzles remind us that our understanding of galaxy formation is still evolving. Astronomers continue refining theoretical models, running ever more sophisticated computer simulations, and gathering new observations from powerful telescopes. Each discovery adds another piece to the story of how galaxies formed and evolved. Yet even as many details remain uncertain, the central role of gravity in shaping the universe remains clear. From the smallest quantum fluctuations in the early universe to the enormous clusters of galaxies seen today, gravity has guided the growth of cosmic structure. It gathered dark matter into halos. It pulled gas into collapsing clouds. It set galaxies spinning and brought them together through mergers. Across billions of years, the quiet pull of gravity transformed a nearly uniform universe into a vast cosmic web filled with galaxies. And even now, that process continues. Galaxies still collide and merge. Gas continues flowing along cosmic filaments. Stars continue forming within rotating disks. The universe remains a dynamic place, shaped by the same gravitational forces that began building the first galaxies long ago. Every galaxy we observe today is part of that ongoing story.